I totally remember this.
Greetings and welcome, friends. Today, we're doing like a straight up flashback lesson to the days of Math 3/Algebra 2. We're talking about simplifying complex numbers, which you might recall are composed of imaginary numbers. In fact, complex numbers in some aspects you could view as hybrid numbers where real numbers and imaginary numbers came together, not unlike Donatello and Leonardo. That will make no sense to anyone on this video, but that's fine. And they made a halberd. I mean, they make a number that's composed of both part real and part imaginary. Now, before we go anywhere, let's first talk about what is an imaginary number. Well, the imaginary unit is the definition of the square root of -1 is defined as being the number I, which is the imaginary unit. Okay, so that is actually a existing thing. It's referred to as a non-real number, but the words imaginary and non-real are actually words that were given these numbers by mocking mathematicians who did not believe in them. Specifically, I believe it was René Descartes, if I'm not mistaken. I believe I've got it right. So the first thing you need to know about imaginary numbers is that the square root of -1 is equal to I, and I squared, as a default, is equal to -1 by definition of a square root, and I cubed, I'll derive that real quick, would equal I squared times I, right? Which is -1 times I, or -I. And I to the fourth, everybody's favorite, you could view as I squared times I squared, which is -1 times -1, which is +1. So knowing these four values is very helpful because I to the first, I to the second, I to the third, I to the fourth, their values end up repeating in a pattern indefinitely, so to speak. So for instance, if I wanted to do, say, this example, which I do want to do, I'll tell you that much. This is how we would do it. So simplify I to the 53rd power. Now I could actually try to break this up into a whole bunch of I stuff and blah blah blah, but I'm gonna try to show you the best way to do this is often related to breaking these down into as many I to the fourths as possible. Why do I like I to the fourth so much? Because it's equal to 1, and 1 is an amazing number to do multiplication and exponents with. In fact, it's probably the best. So I to the 53rd, for instance, using that fact, you might realize I to the fourth goes into 53 13 times. I don't know if you realize that. It goes in that many times evenly, anyway, with a remainder of 1. So right, 4 times 13 is 52, plus 1 is 53. So what I do is I actually ask the question, how many times can I to the fourth go into it? That's how many times it goes in, and then this is my remainder, so to speak. And why is it helpful writing it this way? Well, because I to the fourth is equal to 1. 1 to the 13th power times I is just 1 times I, or I. So I've been able to figure out where in this pattern I to the 53rd lands. So for instance, then I to the 54th must equal -1, I to the 55th must equal -I to the 56th must equal +1. Right, so just kind of continue said pattern. Right, so you might recall doing this from a while back. Here's a question you don't recall, or at least I didn't tell you to recall it. Maybe. It's hard to remember something you never experienced. So simplify I to the -13th. What? So let's figure it out. I to the fourth goes into 13 3 times, or actually better yet, -3 times would give me -12. You agree, right? 4 times -3, -12. and then plus a negative 1. So I to the negative first power. Let's see, so I to the fourth becomes 1 to the negative third power times I to the negative first power. And 1 to the negative third is still going to be 1, no matter what you try to do with that. And I to the negative first technically is going to be 1 over I. And later in this lesson, we'll realize we'd never leave it that way, and we'd keep doing some work to it. I'll come back to that in a minute, though. But notice that I'm able to kind of like rewrite it nonetheless. I'll show you some cool tricks to solve that later. So let's talk about complex numbers, as I was mentioning briefly earlier. I'm not even going to have you write all of this down. But it turns out complex numbers are of the form a plus bi. This form, actually this is a new fact, is referred to as rectangular form for a complex number, indicating perhaps future tense foreshadowing that later on we might have a polar form of complex numbers. What? Mind blown. So in the a plus bi form, if a is equal to 0, or specifically just the a, then all I'd have is a bi left over. That number would be referred to as pure imaginary. And if just the b is equal to 0, then I'd have a number that is just a, and that number would be referred to as real, because there's no imaginary portion to it. Right? Good stuff. So let's do a little bit of work simplifying some complex numbers. And like I said earlier, complex numbers are really just like hybrid numbers, so to speak. Part real, part imaginary, living in both universes. That's just how crazy they are. So, if I'm adding two complex numbers, all I really have to do is add their corresponding parts. So I'm just going to combine these somewhat like terms. 5 and negative 2 combine to be 3. Negative 3i plus a 4i would be plus I. Right? So you just deal with i's almost like terms is really all it is. And if there was subtraction, then I would just be careful to distribute the minus sign to the second complex number, stuff like that. So that's not terribly interesting. What about multiplying? So in order to multiply, I'm actually straight up going to use my double distributing or foiling technique. Right, so because it's binomial times binomial. 2 times 7 is 14. 2 times negative 4i is negative 8i. Negative 3i times 7 is negative 21i. And negative 3 times negative 4 is positive 12i squared. Now, I'm not done yet because there is some simplification that I can do here. For instance, these i's, they are buddies. So we'll pull those together. And question, what is I squared equal to? Negative 1. So this is the same as 12 times negative 1, or a negative 12, which I could then combine with a 14. Intriguing. So 14 and negative 12 combine to be 2, and this is going to combine to be negative 29i. Right, so I do have to just use the fact that I squared equals negative 1. So yeah, these first 4 facts that I gave you are good facts to know, prerequisites, knowledge to do some of these. So, what about dividing complex numbers? And this is where things get a little interesting, not unlike the example where I had 1 over I a moment ago. So here I've got 1 over 3i And the problem is I can't leave an I in the denominator. There's no I in denominator. There is, but you're not allowed to leave it there. Think about that. So what I'm going to do, just like how we weren't allowed to leave radicals in the denominator, I is technically a radical. So leaving it in a denominator is kind of breaking that rule. So what I'm going to do is multiply this by some fraction equivalent to 1. I over I would work where that'd give me like a -1 result in the denominator. But better yet, I actually like to multiply by something that's going to give me an I to the 4th result. You don't have to do that. I over I would work just fine here. So I'm going to multiply by I cubed over I cubed. And I would get spaghetti. I cubed over 3I to the 4th is equal to, now I cubed you might remember is -I, and 3 times I to the 4th is 3 times 1. So it looks like this is just going to equal, I guess I'll write it down here, -I over 3. I was multiplying this because I wanted the 3 and the 1 to add to 4. I happen to like I to the 4ths because they're equal to 1. You would have been fine if you multiplied by I over I. You just would have had a -1 in the denominator. That's all. You also could have written this as -1/3 times I if you want to like try to have it more in that, right, 0 minus 1/3 I if you want it in the A plus BI form or whatever. But seriously, come on. Get over yourself. Who do you think you are? And last crazy concept is complex conjugates, which you've seen this before as well. Does anyone remember what conjugates are? It's when two expressions aren't quite the same, aren't quite the opposite. Their middles are different. They're called conjugates. It's almost a theme song there. So two complex numbers of the form a plus bi and a minus bi are called complex conjugates. And why is that oh so helpful for us? For our last example here, friends. That's why. Do 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 do. So you might recall when simplifying radicals in a denominator, rationalizing a denominator, right? If I had like 1 plus the square root of 3 in the denominator, I'd multiply by 1 minus the square root of 3 over 1 minus the square root of 3 in order to get rid of that radical. The benefit of that was this, that a plus b times a minus b is equal to a squared minus b squared. This is the sum and difference pattern, which equals the the difference of squares. There we go, difference of squares. And notice the nice thing about the difference of squares is that every term is squared. So if I had every term here squared, that would be oh so wonderful, because squaring an I leaves no I's behind. So let's do this. So 2 plus I over 3 minus 2i. I'm going to multiply by the complex conjugate, which is going to be what of the denominator? 3 plus 2i over 3 plus 2i. Good times. And up top, I'm going to literally FOIL or double distribute that, because the fraction bars are a type of grouping symbol. So this will equal 2 times 3 is 6, plus 2 times 2i is 4i, I times 3 is plus 3i, and I times 2i is 2i squared, all over. And in the denominator, I'm not going to FOIL it. I'm going to use this pattern to save me a bunch of time. So that's just going to be 3 squared minus 2i. All squared. And also this pattern always has a minus sign in between it. Right, so I use the pattern in the bottom baiter. Sure. So equals. Let's simplify this numerator. Looks like 4i and 3i. I squared, you might remember, is -1. I'm going to take my time up top because I know I've got multiple steps in the bottom. So 2i squared is the same as -2. I almost wrote I there. 3 squared is 9, and minus 2 squared is 4, I squared. And notice the wonderful thing about another I squared is that's just equal to -1 again. So instead of minusing 4, I squared, that's the same as plus a positive 4 if that I squared becomes a -1, which it does. Oh, how lovely. 6 minus 2 up top is 4 plus 7i over 9 plus 4. Probably don't even have to write that step because you guys are so awesome with I squareds. 4 plus 7i all over 13. And if I could reduce the 13 with the 7 and the 4 simultaneously, I would reduce that fraction as such, but I cannot, and alas, we are done, my friends. You are now masters of simplifying complex numbers, which, theoretically, perhaps you already were.